Hi, this is the second lecture to study the inverse of a Laplace transform. We have in this example x of s defined by the rational function in front of us. The first step, as we explained last time, we got to find the roots of the denominator. The denominator is equal to s squared plus 4, make it equal to 0. We'll find that we have one root at s equals 0 for this one, and this one you'll have plus or minus j2. Obviously, we have an imaginary root here, plus or minus j2. In this case, when you use partial fraction, you will do it in this way. You will have s and s squared plus 4. You leave it as it is. Here you will have a constant, let's say k1. And here the denominator is not going to be k2. Why? Because the order of the denominator here is second order, so in the top should be in first order. So we'll just use as plus b. That's a polynomial of first order. Always, I mean, the rational, you do it like this. And the top part is less than this part. Why wouldn't do it like k2 and k3? Because I don't want to use imaginary number for k. And I'm going to use property or the pair of Laplace transform that uses sine and cosine. Let's see how we'll do that. First of all, how we find k1. K1 is going to be found like normal, You go for x of s and then just don't put s. You have s plus 1 over s squared plus 4. And you substitute by s equal 0. Because you have s on here. So you have 1 over 4.25. So we're done with k1. How you find as plus b, how you find a and b. All what you're supposed to do, just simplify this expression. How you simplify this expression? You do the following. You have k1, it's equal to 0.25 or 1/4. So you can write it 1 over 4s. And as plus b s squared plus 4, and then start to simplify it, have a common denominator, s squared plus 4. Okay, so since we're going to do that, just will be 1/4 will be in the top, 1/4. Why I'm doing that? Because I want to keep the same denominator of the original expression of x of s, which was like that. Here you go, and the top s plus 1. So I can compare in the end. Here, when you have that, so 1/4 will be multiplied by s squared plus 4, and as plus b will be multiplied by s. Now, I mean, the denominator are the same, and I want to compare the numerator. So the numerator I have here on the left hand side is plus 1, and the right hand side I have, just to simplify it, I have 1/4 s squared plus 1 plus as plus, that's as squared, yes, plus bs. So this should be equal. I collect like terms. So s squared has 1/4 and a. So I have 1/4 plus a. That's the coefficient of s squared, plus you have bs and you have 1. All right. When you compare, 1 is equal 1. All right. S coefficient is 1 here and s coefficient is b. So that's the first thing. B is equal 1. S squared 1/4 plus a, I don't have s squared, so it means the coefficient is equal to 0. So we have 1/4 plus a is equal to 0. Then a will be equal minus 1/4. So I got a and b. I just go and put it back in the expression here, as plus b. So x of s now equal, k1 is equal 0.25 over s, and this as will be minus 1/4 s plus b, which is 1 over s squared plus 4. The last step, how to find the inverse, x of t. So what we do, you look for the table. I look for the table. I know that 1 over s, it gives a unit step. So this part will be equal to 0.25 u of t. What about that? This expression, s squared plus 4. When you look at the table, I found something interesting. I found that sine omega t ut, the Laplace transform is equal to omega over s squared plus omega squared. And cosine omega t ut, it gives s divided by s squared plus omega squared. I'd like to tell you about something that will be very helpful. Once you have imaginary root, because you have here plus or minus j, you know that this expression will be a combination of sine and cosine, but you don't know the combination. So you'll make in general, you will multiply this by a. So you multiply this by a, multiply this by b, and then you add them. So you get a sine omega t plus b cosine omega t ut. It will give you the sum of this one will be equal to a times omega plus b times s, and the same denominator s squared plus omega squared. So this expression, it is similar to the second term that we have here, minus 0.25s plus 1 over s squared plus 4. They are the same. The denominator s squared is equal s squared, and 4 is equal omega squared. So I'll say omega squared is equal 4. So the first thing I get, omega is equal 2. Now the top part, you plug omega, so you have 2a plus bs, that's the denominator. The same one here in the top, minus 0.25s plus 1. If you compare, that's the 2a, the constant, is equal 1. So you have a equal 1/2, 0.5. And you compare the coefficient of s is b, the coefficient of s minus 0.25, so b, let's just write, minus 0.25s is equal bs. So b is equal minus 0.25. So you got the value of b and the value of a. So now we can say that the inverse of this term, the inverse Laplace of this term will be equal to a sine plus b cosine ut. And you know the a now. A is equal 0.5 sine omega t, and omega is equal 2, plus b, which is equal negative 0.25 cosine omega t and all ut. So that was the second term. And the first term we already got it, 0.25 u of t. So now we can find the complete inverse, 0.25 ut plus this guy, 0.5 sine 2t minus 0.25 cosine 2t all ut. You can take ut common factor, so you have 0.25 plus 0.5 sine 2t plus minus 0.25 cosine 2t, the whole ut. So that will be the final answer. Of course, you can simplify the sine and cosine to make it one sine, one cosine, but I don't want to confuse you. This is, already correct. The rest is just math if you want to correct.